That's interesting.
Yeah.
You might do us more.
U less, yeah, U less,
Yeah.
yes, yeah. That's usually how I explain it to people. Like when people ask me how it's spelled, it's like the opposite of me what. Oh yeah, that would. I hope that will survive.
Don't like them whiteboards. I don't want them.
We'll figure something out.
Yeah, let's do that. This is finished though.
That one seems to work. Okay. Already made a mark. Okay. Let me just write down the title so that you don't have to go. I'll already have to switch. So we're just supposed to start now, is that the idea?
I can read you this week.
It's all good. My name's Anna. It's easiest. Just put a timer on. So okay. So when I suggested this talk to Wisby, I didn't quite know what the audience would be, and seeing that there's multiple people here who do not know groupoids and their C-star algebras, maybe my talk will go a little differently than I anticipated, but that's okay. Like we'll figure something out. So I'm talking about maximal abelian subalgebras in twisted groupoid C-star algebras, and this is joined with Dana Williams at Dartmouth and Joel Zimmerman, who used to be at Wollongong. I haven't heard from him in years, so I don't know what he's up to now. So in general, like before I actually just introduce you to groupoids, which I will have to improvise, the idea is that I'm interested in nice abelian subalgebras in C-star algebras. And the reason why I'm interested in that is what's called Kumjian Renault's theory, is that if you have a C-star algebra with a very, very nice abelian subalgebra, namely maximal abelian regular with a conditional expectation that's faithful, then you can actually realize your C-star algebra as coming from a groupoid. It's something very dynamic, something very hands-on. So it's not an abstract algebra anymore, but you actually have a model for it that we can understand a lot better, and you can way easier study this algebra than you could before. So this is how I got into caring about nice abelian subalgebras. And so think of C of x or C naught of x within the cross product, if that makes any sense. Some group acting on a space, and then you can look at the commutative C-star algebra that's continuous functions on x, and you have the cross product of C-star algebra where you encode not just the function space, but also the group acting on the space. So this would be a nice abelian subalgebra as long as the action has nice properties. Now, as I mentioned, for me, I am interested in groupoid C-star algebras, so I'm interested in C-star algebras of the reduced type, so reduced C-star algebras, so concretely represented of some groupoid S, and so groupoid is a generalization of a group, and I'll give you a little bit more about that in a second, within a C-star algebra of a bigger groupoid. So some subgroupoid. And I'm interested in when these sorts of subalgebras are in particular maximal abelian. So not just abelian, but actually particularly large, because then they remember more information about the bigger algebra, and they might help us find other models for this C-star algebra. Okay, so let me now try to wing. First of all, does this make sense? Like to an extent at least, without knowing what a groupoid is, thinking just of groups maybe for a moment. Okay, so let me try to wing a definition. So a groupoid G is like a group, but with partially defined multiplication. So for a group, every group would be an example of a groupoid. So you just have your set with your binary operation, and you have so you can compose things and you can invert things. There's a unique identity element that does nothing. the inverses, multiplying two inverses gives you the identity. And the only difference between that and a groupoid, oh yeah, you have associativity obviously, is that for the groupoid, you don't ask for there to be a multiplication defined everywhere. And so the picture that you usually draw is that whenever you have an element of your groupoid, it has a certain starting point and has a certain end point, and then only when that end point coincides with the starting point of the next one can you actually define the multiplication, and that multiplication then is this longer arrow. So you have your G, H, and this is HG, and you have the starting point of G, which is the source, has to be going to the range of G, which better be the source of H. Does this picture make sense? And then this here is the source of HG going to the range of HG, which better be the range of H, source of G. All right. So as I mentioned, any group would be an example. Also, I can just think of spaces as a groupoid where I have no multiplication. I just say all of these points are just lying next to one another and have nothing to do with one another. There's no composition, so that's another example. And a groupoid, then the regular groupoid that you look at is something in between. So you have both the spatial component and the dynamical component where you can move between space. And so another example would be, so suppose group gamma acts on some actual space X, and then I can look at, let's say, gamma acts on the left, alpha X, and then I can take a look at direction I want. I look at this set, so just the Cartesian product, and I make it a groupoid. If I let the following be the definition, I have to figure out how to not mess this up. So I basically just want to encode my group action. Every element in my new groupoid is of the form X, G, and or Y, H. And I want to compose these only if X is actually G acting on Y. And in that case, I want just to go with the range of this element, the range of this element is this guy, which is also the range of that element. And then what I do is I really just use the group multiplication here in my component. So this would be an example of groupoid, and here, this condition here tells me that this is only partially defined. It's not defined everywhere. So I'm only writing down these tuples in composition if I have this condition. Does that make sense? All right, so this is the guiding example that you usually have in mind. So there's this, I don't know who actually said this, but if something is true for this groupoid, it better be true for every groupoid. That's basically the idea, right? So this sort of groupoid is really the thing to keep in mind. All right, and so then, okay, I like to do things not just algebraically, but actually also topologically. So we ask for there to be not just this algebraic structure of multiplying elements, and actually also I didn't actually mention this, inverting elements. I should also be able to go back, right? Not just that, but I also want it to be a topology. So I want the space G to have a locally compact Hausdorff topology so that this multiplication map and also the inversion map are continuous. And in fact, I want a little bit more. I actually want my groupoid to be what's called étale. So G is étale if the maps are the range map, which takes an element and spits out its range. So it goes from this G, it just spits out this number here, or this point. Is a local homeomorphism. So the reason why this is a good notion or interesting topological notion is that I've basically said locally, if you zoom far enough in, you can forget about the dynamics and you're just a space to a certain sense. So in a certain sense, I can, instead of just having like this one arrow that points from this source to this range. I basically have a little set around it where I can do this for an entire neighborhood around this point. But there's really a unique way of going back and forth between ranges and sources. And in the situation of this groupoid that encodes an action, this corresponds to the group that's acting continuously to be a discrete group. Okay, so it's a generalization of being discrete without, like, you're not actually a discrete thing. You have a topology still, but you're somewhat close to being discrete. All right. So that's groupoids. And then for me, the question is, maybe I should, okay. So the next thing is, I should introduce you to at least C-star algebra of these groupoids. Right? So how do you actually go from a dynamical thing like this to a C-star algebra? And the idea is, so given such a groupoid G, we let CCG, so the continuous functions with complex support on G, be equipped with the following product. So I make it a C-star algebra that is not just defined pointwise, like my commutative C-star algebra here, where I really just do everything pointwise and don't do anything weird. But I want a C-star algebra that equips the groupoids multiplication. So I take the function f, and I convolve it with the function, maybe let me say phi and psi, evaluate it at G. What should I get? I want something that really sees the groupoids multiplication. So basically the formula should be split G up in HK, however often you can do this, and then put H in phi and K in psi. So this way your algebra encodes the groupoids multiplication, and likewise you can also encode the groupoids inversion by giving this algebra a star structure. All right, so I'm sweeping a few things under the rug here. So for example, this symbol here, like what I really mean is take G and then write it however you can as pair of two composable things. If you've seen group C-star algebras, it's exactly the same formula, right? And the reason why I can use a sum here rather than have to talk about integrals, why this actually is a sum, comes from this étaleness. But let's also sweep that under the rug. All right, so I have an algebra that encodes my groupoid, and you can close this up. So complete in some norm to get the C-star algebra that I mentioned. So the reduced groupoid C-star algebra. The nice thing is that here I really don't have to talk about the completion. It doesn't matter for most of my talk, but there is a C-star algebra associated to it naturally, which I am interested in. Does this make sense even for the people who haven't seen groupoids at all? At least a little bit? Okay, so if I have this, the question that I was asking is, so when does the subgroupoid of such a groupoid, so if you are uncomfortable with groupoids, think about groups. So think about the integers and some subgroup of the integers. Give me the maximal abelian subalgebra. So when do I get something that's abelian? And when do I get something that's maximal abelian? And the abelian part itself is not so hard. So note, if I look at the C-star algebra of some groupoid S, then this thing is abelian if and only if, and that's maybe not surprising, S is abelian. So if you look at this composition here, if I want phi times psi to be the same as psi times phi, I better be able to move these around, because otherwise I will be able to find functions that don't vanish at a specific point and therefore see the difference between the multiplication. And what I mean for groupoids, I should maybe be a bit more precise. What I mean by abelian, so I mean that S is actually, everything in S is, if something is composable in one direction, but if I can go from G then to H, then I better also be able to go from H to G. So what I actually want is I want loops. Because I want to be able to compose H with G and G with H. So what I have to say is I want S to be inside, or to be equal to S prime, which is all the units and then all the things that start in the unit and end in the unit. What I'm trying to say here is just that I really have a bunch of groups over my space and nothing else. There's nothing where I go from one part of the space to a different part of the space. So this is the first thing, and then ST is equal to TS. Really the natural version. Okay, so being abelian, this is something that's very easily figured out. But then what about maximal abelian? So when am I within my C-star algebra of my big groupoid, the biggest abelian thing that contains? So the next thing is if T is abelian and S is properly contained in T. So say I have a bigger abelian groupoid, then it's also somewhat easy to see that the C-star algebra of the subgroupoid is not maximal because it's contained in the C-star algebra of the bigger groupoid, which is also abelian. And so the reason really is that if these two are not the same, there is an element that lies in my T but doesn't lie in S. Take a function that is supported at that element and a little far away from S. Now that function definitely won't be contained in the C-star algebra because it is supported outside of S, but it is in this bigger algebra, in the algebra. So that might be not very surprising that if you take an algebra, if you take a groupoid that's a little larger, or have one that is a little larger, then you also can't be maximal. And so the natural conjecture is, okay, what if you are the largest thing ordered? What if you are the largest abelian groupoid? Can you be maximal abelian? Are you a maximal abelian subgroup? So at the moment, what I've argued is, if you are maximal abelian as a subgroupoid of G, then your C-star algebra will be maximal abelian among the sub-C-star algebras that come from groupoids. But maybe there's other algebras that are in between. Does that make any sense? Okay, cool. All right. So I'm now middle of the first page. Okay, so at least I have given you an idea of what this is actually about. Okay, so then the question is this enough? Or is this the only obstruction? So is there any way that there can be something in between, like another C-star algebra in between my subgroupoid C-star algebra and the big groupoid? And the answer is actually some bad things can still happen. So consider the situation in which I have some element G in my big groupoid. Okay, that's not better. I'll just go through these pens and see if one of them works. Aha, I have some G and G naught, say, such that if I look at all the conjugates of G by S, so I take my G naught, and maybe let's say this is an element that has the same range and source, so it's a loop at a point. And I conjugate this by all elements in my subgroupoid where I can compose them. And suppose that this is some finite number of elements. So I'm explicitly saying that n should now be at least 1, so I have at least 2 elements that I can get by conjugating this one fixed element. So in this situation, let me actually just say, let's forget topologies. So forget topologies. Just to make our lives a little easier. We'll pretend everything's discrete. And I now look at a specific element, which I write as a sum of point masses. So here what I mean is this is the function defined on my groupoid, which if I plug in one of my GIs, one of these elements, one of these conjugates of G0, I get 1, and otherwise I get 0. Okay, so this is a perfectly fine element in my big C-square algebra of my groupoid. But if my S is abelian, then G0 cannot have been an S, right? If it doesn't commute with all elements in S, right? If I get a G1 out of conjugating G0, then G0 cannot have been an S. So in particular, I'm not in the subalgebra here. Right? So this year, the fact that I get more than one element tells me G0 is not in my subgroupoid. If it's abelian. Okay, so I have an element that is in my big C-square algebra, not in my small C-square algebra. But I claim that A commutes with the subalgebra. And so this tells me that it cannot be maximal abelian. I found an element that is not in the subalgebra, but commutes with everything. Because now you could just take the subalgebra, throw in A, and make a new C-square algebra. It's going to be a commutative C-square algebra that is strictly larger than the one that I started with. Okay, and so what is the reason? It's actually a quite simple computation. So what you do is if you look at this particular thing, by my condition here, so this condition there, if I take any S in S, and then look at the point mass at S, and convolve that with my formula over there with the point mass at G0, or actually just let me say it's GI, one of these GIs, then, I mean, this corresponds to just the point mass at SGI. Because remember, my convolution product is defined in a way that it actually encodes the multiplication in the groupoid. So the multiplication is exactly defined to make this equality true. And by choice of my GIs, they're all just conjugates of one another. So the only thing that can happen is that I pick up another GJ instead. So I can move the S past the GI with the, I have to pay the price of maybe switching my index, maybe going to a different index. This is then DS, BGI, GJ, DS. For some choice of I and J. For any I, there's a unique J so that this equals. What this tells me is that in particular, if I convolve A with my point mass at S, it will go into the sum, and the only thing it does is commute my sum ends. Right? So at the end of the day, the only thing I have done is commute the sum ends, but the sum doesn't care in what order I order these things, and whether I index them from 0 through n or from n through 0 or something. So this particular element, that is just all the finite conjugates, or the finitely many conjugates of G0, the point mass of these, commutes with every element, every one of the point masses, and in particular, it commutes with the entire subalgebra. Because the subalgebra, at least in the discrete case, is generated by these point masses. It's generated by a copy of the. Does that make some sense? So really, the issue is that in my C-square algebra, I lost sums of things. That's the thing. So I'm losing some information as well. Okay, but why was I actually able to write down this element? It's because this set here was finite. This had been an infinite set, then there would have been, and I would have only written down a finite sum of point masses. Then, yes, I would have still commuted them, but I would have not necessarily gotten all of them. Not for every I is one of my J's in my sum within there. The only thing that I could have still made an element is if I had like the coefficients here go to 0 or something. But then, again, I would have maybe commuted the point masses, but not the right coefficients. So this really the only problem that arises here is if I have a finite set here. Because again, the upshot of all of this is, if I am in a situation, without topologies, where I have found an element in my bigger groupoid whose S conjugates are a finite, non-trivial set, then I cannot be maximal abelian, because I can just give you an element that commutes with the subalgebra but is in the sub. Right? And you can just write down, I can write down some easy groups where you see that this actually. It's not difficult to come up with an example, you just need a little bit of torsion for it. All right. And then the question is this all there is? And the answer is basically yes. Just that when you At topology, you have to be a bit more careful because all of a sudden you can't really look at point masses, but you have to look at functions supported around that point, and so everything just becomes a bit more tricky. But so the general theorem, so D. Williams, Zimmerman, 5. So suppose G is étale, and always locally compact Hausdorff, and S is subgroupoid G. And to talk nicely about topology, I want closed and open. And then the following are equivalent. The subalgebra given by the subgroupoid is maximal abelian. The big algebra. This is equivalent to, well, the first thing I have to do is I have to make sure that I am maximal abelian. So S is maximal, or is maximal among the abelian open abelian subgroupoids. G. So this was this argument here, right? If I have a bigger one, then I definitely am not maximal abelian. That immediately can't happen. And then this other condition. Yeah, okay. Maybe I'll have to switch colors. We'll see. And okay, so let me maybe, before I move on and give you a general version of this, let me rephrase this here more symbolically. So i.e., the statement is that if I look at all elements in my groupoid, so that if I commute it with all elements of my subgroupoid, I get a singleton. So I look at all elements in my groupoid that have exactly one conjugate under S, meaning I commute with everything in S, right? This is a different way of saying this. Then this better just be S, as long as I look at this guy's interior, because I'm supposed to be maximal abelian among open subgroupoids. And then the other condition, which is this weird one here, is that you want, and I can't write a nicer condition down that sums it up in words, but the other one is you don't want this. So if I look at all the elements which have finitely many conjugates, but not exactly one. So I look at all the S conjugates of G, and I am not part of S, but I also have only finitely many. And then I look at this set interior, because again, we have topologies, then this better be empty. Then I have none of these. And so the idea is exactly the same as here, just that you have to be a bit more careful with how you brand out the proof. But otherwise, the idea is exactly contained in this. So this condition here, I'm really just, again, pretending you cannot be in a situation where you have an element in your big groupoid that has finitely many S conjugates. Honestly, a single point like this wouldn't be a problem, but an open set like this. All right. I'll let you chew on that for a moment while I erase some words. So this really is the only obstruction. And so for those in the audience that care about Cartan subalgebras, then you can use this to generate Cartan subalgebras, right? So if you have all the other conditions of being Cartan, namely being regular and having a faithful condition expectation, are not that difficult to come by. The regularity comes from normality of the subgroupoid, or at least is implied by it. And the condition expectation you always have when you have a closed subgroupoid. So these two are easy. And so maximality is the one that actually should, if you care about Cartan subalgebras. All right. So maybe in the interest of this sort of audience, I won't go into more details about the proof, which I had originally thought I would do. To just explain how you can bootstrap from the discrete case to the étale case. But the idea really is that you use étaleness to shrink down to sets where this number is actually constant. And then you play exactly this game, that you write down a single function. In this case, it would be the direct point, the point mass at G naught. And then you copy that over it for T times by just shifting the small little neighborhood around that point to the neighborhoods that are homeomorphic to it via the Rankin source. But maybe the only thing that's at the heart of the actual proof, so at the heart is this small little lemma, which is super easy to prove. So if I take a function on my groupoid, or actually these work. So if I take an actual function defined on my groupoid, and maybe here I should, okay, let me just do this. If I take a function in my groupoid C-string algebra, and a function, let's say CC function. Oh, okay, let's do this. If I take an element here, then the following are equivalent. Phi commutes with every f in the subalgebra, and for all elements G and G and S and S, I actually have that where they're composable. Phi of G is actually the same as phi of S G as inverse. So the point really is that the commutant of my subalgebra doesn't distinguish between G and its conjugate and its conjugates by S. So this is the issue basically that you run into, that the commutant can see it, and so if I'm X on the abelian, I better have to absorb all functions that do this. So every function that has this property where it doesn't distinguish between G and a conjugate of G better be in my subalgebra. So in the interest of the people that haven't actually worked with groupoid C-star algebras, forget everything I said and let me just prove this. And so you have at least seen groupoid C-star algebras a little bit, because this is actually quite easy to prove, and it shows you how the convolution product in the groupoid works. So I basically just write down what these two things are, evaluated at some point. So if I take phi of f and evaluate this at some G S, by the definition that I have here, how do I best do this? So will have to decompose my GS into two other pieces. So say HK, let me just write HK. So what this means is that K actually looks like H inverse GS. So here I plug H into phi, this is the first thing, and then I plug the remainder, the K, into F. That's the first guy. And conversely, let's see which ones were there. Yeah, that's better. And phi at GS. So this time I write my GS as HK. So H is GS the inverse. Let me just do this. Sorry. So F of K phi of K inverse GS. All right, so the only thing I've done is I've decomposed my GS, once on the left and once on the right. Here you can see it in phi, V, and F. And now if F is supported in a small enough neighborhood around S, then really I just get a single summand here. Namely, once here I get whatever I need to get S back. So H needs to be G inverse, needs to be G. And here I need to get S. So here this is F of S phi of S inverse GS. And now depending on which of the two things here I assume, if these two commute, so these two are the same, so these two are the same, so now phi of G is equal to phi of S inverse GS. Or conversely, if I assume that these two are the same, so these two sides of the equation are the same, and so these two are the same. Right, so these conditions really are exactly identical. All right, so this is the main issue, and then I have another 5 minutes. So let me just go to the original statement here and just do this very briefly. You can do all of this not just for groupoid C-star algebras, but also for co-cycle twisted C-star algebras or twisted C-star algebras more generally. So instead of just having my groupoid, I could also ask for there to be a 2 co-cycle, say. And in this case, my multiplication is twisted by my 2 co-cycle. And likewise, I get a co-cycle here. And then you can play this entire game for this twisted algebra. And the statement is still true. So you still have the situation where you're in an étale groupoid, you have clopen subgroupoid, then the twisted algebra is maximal abelian in the twisted algebra. You can do this even with general twists. If and only if the subgroupoid is maximal among those where the twist is abelian, and you have this condition just where you have to carry the twist around. So all of this works in the generality of Kumjian Renault theory, so that you can actually apply this to groupoids in the most general setting away from field models. Okay, let me just stop here.
Have any questions for this?
Mhm.
So, always we're working inside the interior of the isotrope,
Yeah.
right? Because otherwise there's
Yeah,
no
that's right.
possibility of being accidental. Do you then, is it automatic that if you've got something in the interior of the isotrope that has a finite conjugate class, then there's a neighborhood of it?
So
This, this triggered local relations thing.
So the trick is that the map that sends, so take your fixed G, you take an interior point in here. Suppose this is not empty, take an interior point, your G naught. Now find the neighborhood where your local homomorphism, or range term is a local homomorphism, right? And now the map that sends a unit to this, to the cardinality of this set, is lower semi-continuous. Therefore, you can find an even smaller set where it's actually constant.
Yeah.
Was that your question?
Yeah, so what I'm thinking is then on that neighborhood, there's a permutation of the G's.
Yeah.
With the property that when I do S, G, S, 5G inverse, I get a unit.
Yes, exactly.
Right.
That's exactly the
And
trick.
now if I choose a neighborhood around each G where that relation holds because multiplication is open.
Yes, exactly.
Automatically, there's
Exactly.
okay. So I don't actually need the interior outside. I just need to know the G's in the interior of the isotrope.
I think you're right. I think you're right. So I think you could also remove this and put interior here.
Gotcha. Thank you.
And that's exactly the trick.
Thank you.
Do you need to change that demo also when you're doing the twisted?
Yes, you do. Yeah. So there's, but it's still true in the same sense, if in the same vein. So if you have twisted C-star algebra, then this is true if and only if when you evaluate at the, so phi of E is sigma E as sigma inverse, so where these are all from the twist. But otherwise, it's exactly the same condition. Yeah.
Local version of that in algebraic setting, like also Steinberg paper.
It's what?
It's Steinberg's paper.
Ah, I see. Yes.
He uses this to get the center of.
Ah, yeah, okay. I've seen this in some von Neumann algebra papers as well. So, yeah. No, I wasn't aware of this.
S there is also a G.
Yes, okay.
Maybe a bit to the side, but is it ever the case that there's a unique Cartan of algebra up to more than 1%?
So the only thing that the theorem that I have with Dana and Joel is showing that you usually can't expect this. Because there's very easy examples. You can just very easily write down groups with completely different subgroupoids or groups that will give you a Cartan that have nothing to do with one another. Really, they are completely different spectrums. I don't think that. I also know of an example that Ian Putnam gave me of a groupoid that has a Cartan which won't come from this. Because it cannot come from a subgroup because it just has the wrong dimensions. So it won't see all Cartans. It's just a way of producing them.
This is not something one would expect.
No, I don't think so, not at all. Oh yeah, I should also mention, because we have a moment, I guess, that I've also have conditions that specify when a subgroupoid gives you a Cicerand. And surprisingly, in the untwisted case, the only choice of a subgroupoid is the isotrope. So no other subgroupoid can give you a Cicerand. As long as, at least if you force more out. I found it extremely strange.